I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
Picking up some dust.
In the 1960s, an impossible dream came true when human beings walked on another world.
The Eagle has landed.
In all, 24 Americans went to the moon. But it took an unseen army of over 400,000 engineers and technicians to make it possible. This is the story of the men and women who built the machines that took us to the moon. Washington, D.C., 1961. And as the implications of Kennedy's speech sank in, many of the country's top aerospace engineers wondered whether it was really possible to get to the moon.
Kennedy's speech shocked me personally, and I was relatively close to what was going on. I mean, it was, wow, can we conceive of doing this? Because we literally hadn't gotten off the ground yet.
The planning in NASA at that time said that we should not have, as part of our program, a manned lunar program. We're not ready enough with our rockets and so on to spend any time on it.
But NASA was in a hurry, and 2 months after Kennedy's announcement, the first Apollo contract was awarded. It was not for a rocket, but for a system that would guide the rocket to the moon.
If you look at all of the prime contracts to build the rockets, to build the spacecraft, to build the capsules, to build the lunar lander, none of those contracts would even be let for months, in some cases years. That's a measure of the importance that the upper NASA administration saw in guidance. How are we going to get to the moon?
The contract went to the Massachusetts Institute of Technology and ran into immediate controversy.
There was actually a budding industry out there that had developed guidance systems, and people from industry were quite upset. They felt that they should have been given a chance to bid on the contract, and a university is not ordinarily what the government contracts out to build hardware for operational systems. Here was a university essentially committing to build a system that was going to fly to the moon.
But MIT was no ordinary university. And MIT's lab, no ordinary research lab. MIT's instrumentation lab was run by a colorful and charismatic engineer called Charles Draper.
An overriding policy of the laboratory is its emphasis on technology of the real world.
Draper was this sort of larger-than-life personality. He had this unique background in psychology and physics, and a lot of people felt that gave him a kind of special insight into human characters that surrounded these types of technologies.
Bob Siemens was one of Draper's early students.
He said, you're not going to have money for the babes, you're not going to have money for the horses, but you'll have an awful lot of fun. There was a big clock on the wall, and he could control the speed of the clock. And all of a sudden, it would be 5:30, even though your own watch might not say 5 yet. And he yelled to his secretary, Marie, come on in, it's time for drinks.
But eccentricities aside, Draper was a single-minded engineer who had caught NASA's attention with a revolutionary navigational aid.
Howdy, Eric.
Hello, Dr. Draper.
He called it an inertial guidance system, an extraordinarily clever device that, in 1953, had enabled him to navigate an airplane from Boston to Los Angeles without any reference to external landmarks.
They put this inertial system, at the time it was quite large, it looked like the size of an atomic bomb or something. Put it aboard an Air Force bomber and flew it all the way across the country.
Chip Collins was Draper's pilot on what turned out to be an eventful 3,000-mile flight.
My job was to get out of the seat and let the system work through the autopilot.
As far as navigation is concerned, we could be flying in a sealed box, deaf and blind.
All went well for the first few hours. Then, towards the end of the flight, Draper's guidance system suddenly appeared to lose its way.
I saw it, and I heard Doc say, "Hey, Chipper, what the hell's going on up front?" I said, "Doc, I don't know, but the system is commanding a turn to the right." Well, there was a big bustle in the back of people trying to decide what to do next, what was happening. Here we were in the 11th hour, and the thing looked like it was going to go crazy.
Yet as the plane emerged from clouds over Los Angeles, it was precisely on course. The guidance system had simply been correcting for side winds.
The system recognized that it was being pushed off course, and it was merely resisting that and doing just what it was supposed to do.
By the time they reached their destination, they were within sight of the airport based entirely on this inertial guidance technology.
Long ways from MIT, sir. Thanks so much for letting us come along. Maybe one could say this is one small step toward the age of space travel.
It was this technology NASA now hoped could be developed to take humans not a few thousand miles across America, but the 500,000 miles to the moon and back. It would be a huge challenge. Spring 1962. And as engineers at MIT got down to work on the Apollo navigation system, their starting point was the university's revolutionary guidance technology. It consisted of a bundle of gyroscopes and instruments for measuring changes in direction.
It looked like a basketball. It's about that size. And inside of it are these very, very precise gyroscopes. And all the gyroscopes do is actually keep the platform perfectly flat and aligned in what's called inertial space. That means not space relative to the Earth or to the Earth horizon, but out there in some abstract idea of place.
The system was based on the principle that when a gyro is set spinning, it remains on a fixed axis, whatever happens around it. So it provides a known baseline, or platform, against which to calculate movement. In this demonstration, the gyros are the rock-solid blue cylinders in the center of the spinning chamber.
Then on that platform are accelerometers. There's a separate kind of instrument that measures the accelerations.
These detect whether a craft is moving forwards or backwards, left or right, up or down, relative to the fixed platform. If you then keep a record of these movements, you'll always know exactly where you are.
It was really high mechanical technology. Draper worked actually closely with the Waltham Watch Company out in the suburbs of Boston, where he taught his people precision machining, mechanical gyroscopes spinning with ever higher precision, very low friction, very low wear. Really, these things were put together like watches, like the most precise watch you can imagine.
Nobody had ever tried to manufacture instruments that would work with such accuracy. Draper imposed new standards of hygiene and cleanliness.
He forbade workers from coming to work and assembling the gyroscopes if they had just come back from vacation in a sunny area and they might have skin flaking off from their suntans. And he wouldn't allow women to wear makeup when they were assembling the gyroscopes.
The most troublesome component was the gyro's ball bearings. Even a minute flaw could, over the huge distances in space, lead to major inaccuracies. Gyro after gyro failed to meet the required standard.
People were clamoring on us, our group, saying, well, why are you rejecting these gyros? You know, how can you keep rejecting them? And meanwhile, we're saying, well, we don't trust their reliability. It didn't take long to feel like, holy mackerel, where am I, you know? After a couple months, I knew that this was a very big job.
Nobody was sure the new system would ever be reliable enough on its own, and so MIT added a very ancient instrument, something sailors had used for hundreds of years to navigate out of sight of land. It's called a sextant. Draper built a simulator on the roof at MIT that enabled astronauts to practice manually checking the inertial guidance system against the stars. But the lab would also need to provide one other vital piece of equipment. Draper's aircraft experiments had used a simple electromechanical device to read the data from the gyros and turn it into flight instructions. The journey to the moon would require something much more sophisticated. They would need a modern digital computer. Yet, to put one of these in a spacecraft was an entirely new challenge. Computers in the early 1960s were huge. The idea of squeezing such a monster into a spacecraft seemed preposterous. Dick Batten was the man who had to do it.
When North American got the job to build the command module, they get on the phone and call MIT and say, understand that there's going to be a computer in the command module. How big is it? And we had no idea how big it was going to be. Right now, it was just a bunch of equipment on a rack. And so we asked around, what do you think? What should we tell them? And I said, oh, well, maybe a cubic foot. Let's say it's a cubic foot.
Batten's new computer would draw heavily on a newly emerging technology that used silicon chips. But the chips were still very new. Manufacturers were still learning to make them, and nobody was sure of their reliability.
One of their tests involved taking all of these integrated circuit chips and immersing them in a bath of Freon. Then they would take them out and they would dry them off and they would weigh them. And if the weight of the chip came out after the bath of Freon, just a few micrograms greater than it was supposed to be when it went in, that meant that some of the Freon must have gotten into a little hole in the chip, and somewhere there was a fault in the chip. And just those few micrograms would indicate that this chip should be rejected and the whole batch would be rejected too.
So that put a lot of attention on making sure every part was built properly and had quality components.
What was special about this computer was people had to stake their lives on it. If this computer failed, if one of the circuits went bad or crashed or had a bug at the wrong moment, people were going to die. And that was really a first, to put people's lives on the line with integrated circuits and hardware. No one had done that before.
At its height, the Apollo program was consuming 60% of the chips manufactured in the United States. But even when they were reliable, their processing speeds were so slow, there were severe limits to the number of tasks they could handle simultaneously before the computer ground to a standstill. For a while, it looked as though the technology would never match the needs of landing on the moon. The man who came up with a solution to the problem was Hal Lanning.
Hal is one of the most brilliant people I ever worked with. He was very quiet, hard to get a word out of him.
He's a very shy person, it struck me, kept out of the limelight. And it was others who spoke for him and recognized his brilliance.
He was someone who everybody at the laboratory knew about and looked up to as a sort of a genius at the laboratory.
Lanning remembers wrestling with the difficulty of computer overload.
I think it was a pretty tough job. I know a lot of meetings were held on the subject of what was expendable, fitting of things together, how things could overlap each other, what liberties you could take.
Lanning's answer was a radical but beautifully simple solution that ensured important jobs got priority.
The high technology way to run computer systems in the 1960s was called time sharing. And in time sharing, there were a bunch of different users or demands on the computer's time, and each one got an equal slice of the computer's time. Hal Lanning really took an entirely different approach, and that is assigning a different priority to each task. So a low priority job might be updating the display to show the astronaut something that was just sort of an indicator of how it was doing. A high priority job is keeping the lunar module upright as it's moving toward a landing. And then if you got into trouble, you could drop the low priority jobs, keep the high priority jobs running.
Yet as the computer evolved, there was confusion at NASA. The technology was so new, nobody was sure exactly what it could do. Should it provide the navigation for the entire mission, or was it primarily an aid to the astronauts?
Over the course of the 1960s, you see groups of astronauts and groups of engineers at the instrumentation lab really working together, almost negotiating out a role for the human operator.
It was a fundamental confusion that would, in the years to come, cause serious problems for the newly emerging breed of software engineers. What kind of computer programs would they need to write? What would they need to do? And how many would there need to be? In the early 1960s, as work on the Apollo computer and navigation system got underway, software was an almost unknown concept.
I went home and told my wife that I was in charge of software. And she said, "Please don't tell any of our friends." It sounded like a real nothing piece of work.
The word was barely invented at the time, and the original contract for the Apollo system says, of course, the instrumentation lab will write the programs that will run the thing. It turns out that software became one of the major defining problems of the system.
With nobody clear on exactly what the computer should do, the software engineers were free to write almost anything they liked. At least at first.
There were no specs. We made it up. And it's always amazing to me, why was I allowed to program something that hadn't even been specified that would be critical in assuring the success of the whole Apollo program? I couldn't believe it, but that's the way it was. We made it up as we went along.
The lack of specifications led to a proliferation of software routines at a time when programs were agonizingly laborious. Each program was written by hand and turned into punched cards a computer could read.
If you submitted a job during the daytime, it was likely to be hours before your output would appear on the table outside the computer room.
We could stand there and watch it and wait for it to come out as a line printer output. It was maybe 1/8 of an inch thick. If you screwed up, you got an output that was maybe 2 feet thick.
But the real problem was not the glut of paper. It was memory. The computer simply didn't have much.
The overall memory for the Apollo guidance computer program was equivalent to 72K kilobytes, 72 kilobytes of memory in modern terms.
Today, a $100 MP3 player has 50,000 times more storage space. Furthermore, the computer disks that stored the programs were fragile and unreliable. The solution today seems extraordinary. It was called rope memory.
You actually had to send the program to a factory, and women in the factory would literally weave the software into this core rope memory.
We called it the LOL method, the little old lady method of wiring these cores. Not a very nice. Today you couldn't say that. say that.
Computer code consists of ones and zeros. In this case, it was a physical distinction. Margaret Hamilton was one of the very few female engineers on the project.
The rope is made up of rings and wires. And if the wire goes through the core, it represents a 1, and around the core, it represents a 0.
It was extremely slow. One program could take several months to weave, and if there was an error, it was a nightmare to correct. The software program was falling dangerously behind schedule.
Everybody was running behind. We weren't the only ones. But it became more and more nerve-wracking to Houston to see what are those MIT guys up to? Are they going to pull this off?
It was becoming painfully clear that everybody had dramatically underestimated the scale of the job facing Draper's lab. In 1966, NASA sent in a troubleshooter.
Bill Tyndall starts looking at the Apollo software and ringing alarm bells. In fact, he writes back to headquarters and says, "I worry that we might not make the end of the decade deadline for the moon landing because the programs won't be finished." Very strong statement when you're building these enormous rockets and you're building launch pads and you're training astronauts, and then a bunch of programs might keep you from getting to the moon on the president's deadline. Very, very unusual situation.
Bill Tyndall started going through the lab's work with a fine-tooth comb. He found widespread duplication in the software that made it grossly inefficient. It was slow, full of bugs, and was outgrowing the available memory.
He began writing this series of memos from Cambridge, where he would come visit, back to the NASA headquarters, which are known to this day as Tyndallgrams. They basically said, MIT is screwing this up. They're not paying enough attention. They don't have the discipline of a large organization. This is not a research project anymore. They really have to get serious.
Tyndall started knocking heads together.
Bill Tyndall came to the laboratory on Friday the 13th. It was already bad news.
We all resented these guys coming in here and ripping our baby apart.
He really put our nose to the grindstone and really kept bird-dogging us. That is, this is what you said last week. What are you going to tell me next week? This is, you told me it was going to be ready now. When is it going to be ready? And so on. And he kept pushing this in our face to the point of being, we thought, extremely arrogant.
As programs were discarded, there was a whiff of rebellion.
People at the instrumentation laboratory, in one case, actually rebelled. We actually had, I can recall, a meeting where we all got together and actually complained about how difficult it was to work under this environment.
By mid-1966, Draper's dream of an onboard navigation system that ran the entire mission had vanished.
They now said, we will make the navigation from the ground primarily. We will use the radio waves as the primary source of navigation, and the onboard computer will be essentially the backup.
The astronauts would now get their principal navigational data from radio signals from the Earth. Yet Draper's guidance system would still be their only backup on the far side of the moon, or if the radio signal failed altogether. But would even the demoted system be reliable enough? And would it ever be ready on time? (1967), and with the deadline for landing on the moon getting closer, the instrumentation lab at MIT was struggling to meet its schedule. Engineers began to put in long hours. Too long for some of them.
In my personal case, I think that contributed to the end of my first marriage.
Almost all of us are divorced that ended up doing that. I don't know that that's directly responsible, but it's probably more than a coincidence.
My wife said to the kids, they were youngish then, "Guess who's coming to dinner tonight?" "Daddy?" That was their response, because it was a fairly rare event that I was home for dinner.
Finally, after one of the hardest years many at MIT could remember, the computer had been squeezed into what looked like a small refrigerator, and the software had been tested to exhaustion. In October 1968, Apollo 7 became the first successful manned Apollo mission. For 11 days, 3 astronauts orbited the Earth, using the sextant to check the automatic guidance system. It worked perfectly. It was time to take the next step.
We have ignition sequence start. The engines are on. 4, 3, 2.
On December 21st, 1968, Apollo 8 took off from Cape Kennedy and headed into space.
p.m. Eastern Standard Time.
It was going to be the first attempt ever to send men around the moon. At the Draper Lab in Cambridge, tension was high.
Well, it was more or less unbelievable. You were trying to think, you mean this stuff is all finally going to work?
They kept announcing what the velocity of the spacecraft was, and it was getting bigger and bigger. And I turned to the guy next to me and I said, my God, they're really going to do this.
It's very hard for me to convey to you at this time the level of excitement in that room. It was like listening to every syllable of every word that the astronauts might say.
Transmission is coming to you approximately halfway between the moon and the Earth. We have about less than 40 hours left to go to the moon.
As the astronauts headed towards the moon, they checked their position over and over again.
Jim Lovell decided that he would show that you could do navigation on board the spacecraft using the sextant, and he did that many times, actually, and demonstrated it worked extremely well.
Then, as Apollo 8 disappeared behind the moon, all communication with Earth vanished. Now they would be entirely dependent on the MIT system.
Everything went blank for a while. And you had to wait, and you knew when you would pick up their voice again if they were in lunar orbit, and you know when you'd pick it up if they never made lunar orbit, or if they were halfway into lunar orbit, which would have been even worse.
We all knew what instant of time there would, if everything went right, when we would hear from them again.
We just sat there for 45 minutes waiting to hear whether this was a success or not. And after 45 minutes, the communication officer at Houston started to call the Apollo spacecraft.
Apollo 8, Houston, over.
Apollo Control, Houston. Jerry Carr has placed a call. We're standing by.
No one answered, and so everyone was pretty concerned.
Finally, just a little bit after we expected to hear from him, there was a voice.
Go ahead, Houston, Apollo 8. Very complete. Our orbit is 160.9 by 60.5. Apollo 8, this is Houston. Roger. Good to hear your voice.
Apollo 8 had re-emerged, right on schedule, and was back in radio contact. Seconds later, MIT's computer relayed back its on-board calculation of where the spacecraft was. It corresponded exactly with NASA's Earth-based calculations.
There was a tremendous amount of relief in the room, a lot of cheering, a lot of satisfaction that what we had produced actually worked.
For the engineers, it was the vindication of years of hard work and broken marriages.
I remember watching it at home, Christmas Eve, 1968. So I was like, a million other people that watched the same flight. Brought tears to the eyes. That it's doing it to me now. Even just sitting at home, watching it on a little TV, black and white, it was we did that, staggering thought.
But now the computer that had helped them around the moon would have to do something even more demanding. It would have to land them on the moon.
And you're maneuvering, right? Will be shortly.
July 21st, 1969, and Apollo 11 was 3 days into its mission to land on the moon.
Apollo 11, Houston, we are go for undocking, over.
As the lunar module separated from the command module, Armstrong and Aldrin were 12 minutes from the lunar surface.
You got a fine-looking flying machine there, Eagle, despite the fact you're upside down. Somebody's upside down.
They were about to draw on an entirely new software routine never fully tested in space before. The program without which it would be impossible to land on the moon. Yet, incredibly, the program had been written almost as an afterthought by a junior engineer.
If you talk to the guy who really wrote a lot of that software, Don Iles, here's this 22-year-old guy, gets his first job. The program is already 2/3 of the way complete, and they assign him to write the programs to do the actual lunar landing.
There was always a trade-off of time versus memory. You could always write something quicker if you could use more space to do it.
It wasn't just brand new. It was one of the most complicated routines MIT had ever written.
Neil Armstrong said, in terms of a scale of 1 to 10 of difficulty, walking around on the moon was about a 3. Landing on the moon was a 13. It was the most complex series of continuous operations in the entire Apollo mission.
As the lunar module dropped towards the moon's surface, everything seemed to be going smoothly. But then, out of the blue, there was an alarm.
Program alarm. 1202. 1202.
When we got this first program alarm, and that was total news to me.
1202 alarm. Yeah, and the same thing we had.
Then more of these alarms started to show, and we got extremely nervous. Everybody in that room, management and programmers listening to this, not knowing exactly what was happening and not knowing what these alarms were. Maybe some people in the room know what a 1202 alarm was, but I don't remember anybody popping up and saying, oh, I know what that is.
With only seconds to go before landing, the astronauts asked for advice. Should they abort the mission or override the alarm?
Give us a reading on the 1202 program alarm.
I was panicked. They were actually going in close to the moon, landing, and they were getting a 1202 alarm. No way that should have been happening.
As concern spread through mission control, one man put his hand up. Jack Garman had the only summary of the alarms in the building.
I wrote them down in pencil on a piece of paper, every alarm, what it would do. I taped it to a piece of cardboard and I stuck it under the plexiglass that was on top of our consoles. You know, it's like an umbrella. If you carry it, it won't rain.
We had a nickname for Jack. He won't forgive me for saying this, but we call him Garflash.
You know, I haven't heard that in a long time, but yeah, Garmin, Garflash. I did tend to react rather quickly sometimes.
Garmin's note told him the alarm indicated the onboard computer was overloaded.
Executive overflow, it was called. That is, the computer did not have enough time to do its work. Thus, it was overflowing, and it spewed out this alarm.
A normal computer would have ground to a standstill. But thanks to Hal Lanning's revolutionary operating system, the lunar module's computer was simply dumping low-priority jobs and carrying on with the important ones. There was no immediate threat. Garmin gave the OK to land.
Okay, all flight controllers, go for landing. Retro, go. Fido, go. Guidance, go. Control, go. Telcom, go. GNC, go. Ecom, go. Surgeon, go. Capcom, we're go for landing. Eagle, Houston, you're go for landing.
Yet, as the lunar module touched down, the big unresolved question was, why had the computer overloaded? And would it compromise the return journey?
The expression out of the frying pan into the fire comes to mind because there was no time to think, really, for anybody. It was time to get on with the checklists and procedures.
It wasn't, I would say, 15 seconds after they land that we have Houston telephone wanting to know what is that 1202 and 1201 alarm.
I saw Fred Martin across the room, and our eyes locked. It was like, oh no, what is going on? Why are these 1201, 1202 alarms happening?
She looked at me and I looked at her.
Not really seeing anybody else in the room, but more of registering, we've got to find out what this is.
In all the testing that I had witnessed and all the things that I had witnessed at the laboratory, I had never seen one of these alarms come up, so I didn't know what it was about.
Eventually, they discovered the problem. Buzz Aldrin's checklist had instructed him to turn on the return radar too early, and the computer had simply been unable to handle that as well as all the immediate landing data. It was a checklist error. The computer had worked exactly as it had been designed to.
9, 8.
They were safe to return, and after nearly 22 hours on the moon, Armstrong and Aldrin were given the go-ahead to return home.
Very smooth.
Two and a half days later, with the support of the computer guidance system, the command module crashed through the Earth's atmosphere at precisely the right angle.
I had teared up because of that, but I think a lot of people did. It was the culmination. That moment was the moment. As much as Apollo 8 was the biggest step, perhaps, that moment was it.
You know, I remember more about the 1201, 1202 alarms than I do when it finally landed back on Earth.
The relief at MIT was overwhelming.
Everybody was just super happy that we were successful. And we were super happy.
It was the end of nearly a decade of some of the most fruitful and creative computer engineering in U.S. history. For many who took part in it, it's still the most remarkable thing they've ever done.
I spent a good chunk of my life working hard to produce guidance software that enabled that to happen and that they left behind. So sitting on the moon is code I wrote. It has always been my proud boast. Something I did is sitting on the moon right now. That is a neat thought.